title of the talk, No Pain, Some Gain, Boosting Your Work Through AutoML and Relational Learning. That's more the catchy part of it, but what do we actually do? So me and myself, Patrick, Dr. Patrick Urbanke and myself, we were both working as data scientists for a big car manufacturer back in the days. And we realized that there's one significant part of our daily work that is boring and that we pretty much hate. It's called feature engineering. So basically sitting down and coming up with lots and lots of feature ideas and building an algorithm for that and putting that in another algorithm. So we thought, well, it would be nice to automate that. And that's when we started working on the very basics with getML. Right now, we sit in Leipzig, as already mentioned. We're a team of 7 people in the Alte Spinnerei, and are working on that problem. So what I just described is basically what everyone else think is automated, so that machine learning still needs a significant amount of human assistance. So basically us as data scientists preparing data before AutoML can actually take over with training and predictor. And if you for a second imagine that you're a data scientist and that you're working for a big bank, you might be confronted with that kind of problem. So based on historic customer data and customer behavior, you should train a machine learning algorithm depicted by that very nice robot in that case that can predict whether a customer is likely to default or not likely to default. So if the customer is going to pay back his loan at one point in the bank. And that's what, like, you as a customer typically would expect, but what is it that we as data scientists then have to do? So let's talk about the perception versus reality of machine learning. We still have our picture of that nice robot on the left. So basically how everyone else except us understands machine learning. And then there is that brutal reality. So in that case, the basically logistic regression that we use to actually train and build an algorithm that can come up with a prediction. And to put it in really, really simple terms, what's the difference between these two versions of machine learning? Yes, the function on the right-hand side is missing its arms. So what we as humans and basically people less familiar with machine learning typically expect is that these are highly versatile algorithms that in a blink of an eye can be adapted to something new. But in reality, and also to put it in very simple terms, the data has to fit into that X. It has to fit into the functional term. It has to be the vector size has to be in the right length that we can actually estimate these weights. But why is it that difficult, like, to really point out that it's not that versatile? It's because of the nature of data, the data and its structure that is surrounded and that people expect data scientists to train their algorithms on. So there's on the one hand side text, there's speech and video content, there are images, and there's relational data. And if you really think about these major 4 kind of pillars of different data, is that it's stored in very different ways and that information is represented. So basically the data that the pattern has to be found inside from that algorithm is very different. And coming back to the very simple example, it's really hard to fit raw data inside a function that is that versatile to come up with predictions straight away. So at the end of the day, before we can start with machine learning, we somehow need to reduce that raw data into something that can be used as a basis for supervised learning. Again, it's in simple terms, what I just called preprocessing is what everyone understands with under feature engineering. So basically coming up with merge and with ways to reduce that data. Sorry, I was skipping something. And then, but let's think about an let's think about deep learning for a second. So right now on raw data that is of the type text, videos, and images, machine learning already works quite well, and that's due to the fact that there's an algorithm that can automate that preprocessing that I just described. So to basically make pictures fit into the predictor, and that can do that basically autonomously. And that's what these deep neural networks are good in having these deep feature cascades in really really figuring out important indicators in the raw data that helps then to make a prediction, for example, if it's a cat or a dog inside that picture. But unfortunately, the raw data that we are usually surrounded with in big companies, so relational data, doesn't work with neural networks. So the kind of the structure of relations is something that is like simply not possible to propagate or to work through with these matrix multiplications, max pooling operations, and the learning of weights. So basically what that feature engineering aspect of neural networks is good for. Instead, it's us humans that have to get back to the drawing board and do that kind of preprocessing. So now it's us that have to decide what is important and what is possibly connected with the outcome. So with the outcome, if a customer is going to pay back his loans or whether that loan is going to default. And that knowledge is like, first of all, really hard to gain. So it requires a lot of process and product understanding, something that we're most of the time not really trained for. We as data scientists are good in statistics. We have developed capabilities of working with algorithms and an understanding of hyperparameters, for example, not about the underlying business case that these algorithms are most of the time trained for. So like going back to that very simple example of cats and dogs, no data scientist right now is required to exactly know the differences between, I think, the close to 140 different species of cats that the latest Inception architecture from Google was trained on. And with that comes the problem that the kind of features, so that feature engineering, data wrangling, is quite actually ugly to code. So it's not one feature. You have to write hundreds of scripts to really get a good predictive accuracy of the predictor that you later on train on top of on that feature set. And thirdly, which is in some sense frightening, if there are a lot of known unknowns. So if we don't know what feature to look at and which features will bring up the predictive accuracy of the machine learning model that is trained on top, that the lack thereof will lead to potentially underwhelming and an underperforming model and bad predictive accuracy. And given that sometimes we're interested in the latest fraction of a percent to tune the accuracy of our model, I think that's the step where the potential is the highest to actually increase that predictive accuracy. So at the end of the day, that's another image of a manual feature. So on the left-hand side, you have that relational data that I just talked about. In the center, you have one SQL feature. It's a very simple SQL feature that is displayed there, but the idea gets across. So it's choosing an aggregation function over a certain relationship between the population table, so the table that contains the statistical population, basically the foundation for supervised learning, and a transaction table. And then you come up with conditions. And at the end of the day, if you have to go through manual feature engineering yourself, you write hundreds of these kind of features to extract from relational data a flat feature table that you then put into AutoML systems, or just into your basic connected with manual feature engineering. We thought ourselves, well, it would be nice if we can automate that. If there is a way to generate or to have an algorithm decide which merge and aggregate operations are really necessary to get up the predictive accuracy of our model. So the objective is really to automatically generate that flat table from a relational data model, and we, as data scientists, are required to literally don't have anything else than an understanding of the data model. So something that in a best case scenario you have in your database system readily available, that you have a clear idea, of course, what you want to train on, though, so the target variable. And another condition is that we don't want to have any expert knowledge on the kind of patterns that are really visible in that event, and that can that correlates with the outcome of the prediction. So we came up with an algorithm. So basically, it was a tough mathematical problem to solve. We came up with a solution. It's called MultiRel. It's one of our algorithms that you can use for feature learning or for automated feature engineering, that comes up with that flat table based on relational data. And MultiRel itself is based on the idea of gradient boosting, but I will get to that in a second. Let's look into the parameters that MultiRel can tweak. So, of course, as data scientists, even that we are happy to work with black box models, we also would like to understand kind of what they're doing. So when we decide designed these algorithms, we had our physical approach or our manual approach in mind when we decided what kind of parameters needed to be tweaked in an automated feature engineering use case. So here in that case, what is highlighted in that picture of the feature that you just saw 2 slides earlier is the aggregation function and the join key. So these are the first 2 things that the algorithm can freely decide on. So given that relational structure, the knowledge of the relational structure, it's up to the optimization criterion which aggregation function over which join key is been taken into account for further optimization. And then it's just a simple bootstrap/bagging approach where we train these different features inside. And then the second thing that like increases the predictive accuracy of that data wrangling or of that merge operation that I showed you the slide earlier is the condition. So the combination of multiple numerical and categorical conditions is what usually is done to increase the correlation of that feature with the outcome. So as humans, we take, or most of the time, start with simple values that are somehow related to the way we think about time. And here in that case, we only aggregate over that transaction value. So we take the sum over the transaction value T2 if the reference date, so if the transaction and the date when we want to make the prediction is not more than 90 days apart from each other. But why 90 days? Why can't it be something more cryptical like 45.37 days, which might, in case, bring up the importance of that feature at the end of the day. So, and now coming to the working principle of the algorithm is that these are the more or less the recipe that that algorithm follows. So first of all, we pick an aggregation over a column. So and then we have one optimization criteria and add different conditions, or that algorithm adds different conditions to that feature to bring up that objective that we try to optimize. So we increase the there's another important part that I forgot to mention. So it's we add these incrementally. So the objective function that we are estimating in that case, or that the algorithm is estimating in that case, can be iteratively updated. So when the algorithm decides to take another condition into account, or increase the offset of a parameter, in that case 90 days, by in delta, then we don't need to calculate or start calculate over what we already got. So it's an incremental way that algorithm searches for an optimal aggregation function over a specific join condition to maximize the improvement of that objective or of that criterion. And then at one point, when we added enough of these conditions, the stopping criterion is met, and we start with a different feature. So then, given on the number of hyperparameters that Johannes will speak about later, the number of features can be influenced. But how does like an automatically generated feature looks like? So that's an example. That's a real-world feature generated with MultiRel on an slightly different prediction problem. So there are definitely some features that are familiar to us. We have an aggregation function. We have a left join of two tables on each other. And then we have that group by operation. Then, of course, there is that fixed condition that the timestamp of one of those of the population table should always be larger than the timestamp of events that we are aggregating on. But the real power of that feature is the part that we could understand if we really spend a lot of time onto, namely what these different categories mean. So why it's actually important to exclude a certain set of parameters or to include a certain set of parameters. But at the end of the day, that's the feature that we would be able to understand, but never be able to come up with ourselves. And that's, again, generated with that based on the idea of that MultiRel algorithm. So at the end of the day, we included algorithms in getML that have the ability of preprocess that raw data, so relational data set, and bring that relational data set down to a flat feature table that then the machine learning algorithm can be trained on. And of course, as most of the times, if there are two algorithms, it's easy to combine them and to do both in one single step out of one software framework, and that's what getML incorporates. So the core functionality of getML is really the feature engineering, but getML also does the machine learning part. So that's why we think getML enabled the deep learning method on relational data. So that's how getML looks like at the moment. You can download it basically straight away on our homepage. It comes with an MIT licensed Python package that is available from pip. And if you installed getML, created your user account, and installed the Python API, you're basically ready to work through the Jupyter notebook that Johannes is going to show you in a minute on your own, as well as adopting it to your own and very individual needs. All right, that's it from my side.
Yes, thanks very much. I hope that many of your questions will become even clearer now that I go through a real world example using getML. And I think it's a very good addition to the journal introduction. So after this, everything should be crystal clear, and if not, then there will be more time for questions. So what are we looking at here? This is a use case from financial sector, as Alex said. So we want to predict loan default. So we have a list of customers from a certain bank, and each of them took a loan, and now we want to predict whether or not they will default or not. The data for this project is publicly available here from the Relational Learning repository. So you can go after this, you can go download it and basically go through the material on the getML GitHub repository that will be shown soon, and then do everything yourself and make sure that I didn't cheat or anything. So this data set contains 606 successful and 67 unsuccessful loans, along with some peripheral information. And the data scheme is shown here. So we have one population table with the information about the loans themselves. So this would be like our statistical population that we want to make a prediction about. And then we have two peripheral tables, one containing transactions and one containing permanent orders. And both of them can be related to a certain loan via this join key called account ID. And so this is basically where the problems start, because now if you wanted to start training a model on this population table, you would have to come up with a way to make a join between these tables and to add the information from these two peripheral tables to the population table. And the obvious problem here is that there's a one-to-n relation between one loan and transactions, because each of the customers having a loan makes multiple transactions and has multiple permanent orders. And there you are sitting there and having to come up with SQL statements to create features to even get started with machine learning. So this is again the very problem that we try to solve with getML, that we solved with getML rather. Okay, this is the boring part. We just read in the data. And this is very interesting because, as Alex said, we need to know beforehand. So what we have to put into the algorithm is the information, what we want to predict. And in getML, this is done by assigning roles to each column. So here we tell the algorithm that the column default in this population table is our target. So this is the column we want to predict. And similarly, we continue for the other columns. So we tell it that the column account ID is the join key of the analysis, and that there are three more columns called amount, duration, and payments, which contain numerical values. And there's another column, date, that contains a timestamp. So this is basically the start of the loan. So this is in order to later make sure that we're not using any data from the future.
Sorry, Johannes, can I interrupt you for a second? Can you zoom in a bit? The video quality is quite bad, at least on my side. So just one more step or two. Okay, perfect. Now it's still not very sharp, but I think that now everyone should be able to.
Can we make a poll or something if anybody can read? Because if not, then I have to approach the whole thing differently. Well, I'll just continue, and then if it doesn't work at all,
I think it's better now. I think it's better now. Before it was very blurry, but now people can read it.
Okay, great.
Okay, perfect. Thank you.
Okay, thanks for the hint. Okay, and as already discussed before, we need to have a training and a testing population. So I split the data set before into a train and testing set. Yeah, so this is the population table that I've just loaded. I mean, just here's the default column 0, 1 Boolean value, obviously, a date, and here these numerical values and a join key. So far, so good. We do exactly the same with the two peripheral tables I mentioned. So one is the transactions table, again with the join key, obviously, because you need to join into the population table, a timestamp, and in this case, 4 categorical columns and 2 numerical ones. And this is actually quite nice to see, because as Alex said, we don't want to have any expert knowledge in finance here. And in this case, we can't, because it's in Czech. So I have no idea what these categorical values mean. I just know that they are categorical, obviously. And I made sure that they make sense in the way that the number of distinct categories is not too large. But apart from that, no other information is made available to the algorithm. And the same goes for the order table. So 2 categorical columns, 1 numerical one, the join key, and read from CSV. And this is what it looks like. Okay, so this is one ingredient. All the data were annotated with roles. So telling the algorithm, okay, this is, as I said, the target, this is numerical, and so on. And the other input is the data model. So we have to tell the algorithm, okay, how are these tables actually related? And this is done via placeholders. So I create placeholders for each of these tables, and then I do an abstract join between them using this join method. I tell them, okay, there's a join between order and the population on this join key. There's a join between transaction and the population on this join key, with a temporal constraint that the timestamp in the transaction must be in the past with regard to the timestamp in the population table. This is what this placeholder now looks like. So this is the training population, and it has the information here that there are two joint tables, and the order and transaction. I mean, I guess it's data model should be pretty clear by now. Maybe let me pause here a while and show you something that was shown on Alex's slide briefly, namely the monitor. So this is a graphical interface that runs in the browser that helps you debug your analysis and have information about what you've actually done. And so far what we've done is read in the data. So we see here that the 4 data frames we've read in, the training population with 460 rows roughly, testing population with 220, and then the transaction here with 1 million rows. So this is by far the biggest table. And there's here some overview on, I mean, in this case, it's pretty easy to keep track, but once you do an analysis with 10, 15 tables, this can come in really handy. So just to let you know exactly what is going on. Okay, this is it. Now we have defined the data model, read in the data. Now we can start training the model. And to this end, we choose a feature selector, in this case, XGBoost, and we choose a predictor, again, XGBoost. So these are both, so once we have trained the features, we will run these feature selector and predictor to do the actual prediction, and using this loss function, so cross entropy loss. And so this is how you would instantiate the MultiRel model. Just like this, and the information you have to give it is the aggregation space it can use. So here we tell it, so it can create features by taking the average over a certain column, count, max, median, min, sum, or variance. So this is these are all the aggregations that the algorithm will use to create features. We tell it to create 30 features. I mean, in a real world analysis it would be more like maybe 100, 200, but for this use case, I wanted to keep it simple and make it run quick. And okay, here we communicate the data model and our loss function, feature selector and predictor, all pretty straightforward. And that's it. So now we can start fitting the model to the training data. So this is where we give the training data, and as you see, it finishes under 1 minute. So it's really quick. I mean, from defining the data model and annotating the data to getting a first estimate, this takes maybe half a day to complete. So this is kind of the nice thing when starting new use cases, that you get to results pretty quickly. But before I brag too much about the results, let's look at them. So we score the model once in sample, so on the training set, and out of sample on the testing set, and you see that the in sample accuracy is out of the box pretty good, and also the AUC. But an out of sample, okay, in this case it's even better. Usually you would expect that it's kind of worse because of overfitting. But nonetheless, typically we wouldn't stop at this one iteration, but as Alex said, go on and do hyperparameter optimization. This is built in here using Latin hypercube search. And so these are all the hyperparameters that are used to regularize and tune the MultiRel model, and I give it a grid here that it can use to search the best place in the hyperparameter space. And then I define a Latin hypercube search here. So if there are questions about Latin hypercube search, I can answer them later. It's basically a very brute force way to optimize hyperparameters. There are more sophisticated ones built in the software, but for this introductory example, I will use this most simple one. And again, here for sake of runtime, 5 iterations only, I fit it, and then I get the best model and look at the scores again, and as expected, well, I mean, it became better, but it became much better now. I have 69% accuracy and an AUC of 49. Okay, so this is the results that come out of the algorithm. At the moment, it might look like black box magic, but this is also a very nice feature of the monitor, because now I can actually have insights and look at the features that were actually created. So these, I will zoom out a little bit again. These are all the models that were trained in the process. So these are the 5 models that were trained during the hyperopt session, as you can see here. And if I go for the one with the best AUC, so the one that I chose in the end with the 69% accuracy, now I get some information what happened behind the scenes. So this is the RC curve that I guess you know, and here is the information about all the individual features. And I guess this is the most interesting plot. So it shows the feature importance for each of the features. But so most interestingly, I can now look at the feature with the highest importance and check out the SQL code that was generated by the algorithm. So this is really the kind of the foundation of everything. This is the feature that was created on this data set, because I mean there was a question before, can you show a feature on the data set? So here's one. And what did it do? It chose to left join the transaction table here and use a variance aggregation over this column balance using these subconditions. So there's nested subconditions that take into account the numerical columns, but also the categorical columns. And yeah, as Alex already said, I mean, this is a feature that you can easily understand when you look at it for a while. I mean, you can at least you can understand the concepts behind, so what it roughly did, but it's something that you could never come up with by hand. So if I in the beginning I had sat down and thought about, okay, how can I aggregate the transaction table to create a feature for this analysis, then this is probably wouldn't have been my first guess. And using the MultiRel algorithm, it was generated automatically for me. So I hope that this example illustrated a little bit more how this whole concept works and what the benefits are. And now I'm happy to take